Welcome to the next video for our core quantitative methods course. This time I'm going to introduce you to some different ways of conducting quantitative research and to then ways of thinking about the quality of research that has been conducted. And then I'm going to focus for now on hypothesis testing. Clearly, descriptive research is interesting to see how things are in the world, but most of the time we might have specific beliefs and then we want to test these beliefs. So we come with a specific falsifiable hypothesis and then we start looking for data that is able to disconfirm the hypothesis. If the data that we find is sufficiently close to what we expect, we might say the hypothesis is retained as provisional knowledge. We can never prove it, but we can say it's the best knowledge we have at the moment. And then we can decide if we try to collect more data to keep on testing it, or if we come up with the next, maybe more specific hypothesis and move ahead in our research agenda. If the data does not conform to our expectations, it might be time to reject the hypothesis and move on to a new hypothesis. This whole notion of hypothesis testing is at the very heart of inferential statistics, so it will be very important in parts 2 and 3 of this course. But it is at the heart of how we think about most quantitative research. In that generally the most interesting type of hypotheses are the causal ones. So hypotheses of the type that something causes something else, using Instagram causes social isolation. Those are better than pure associations because they allow us to see how things are related and give us a first indication for how we might be able to change things. In such a case, we have special names for the variables. The variable that we hypothesize to be the cause is called the independent variable. The hypothesis that we expect the variable that we expect to be the outcome is called the dependent variable. So in the case I just mentioned, Instagram usage would be the independent variable, and social isolation would be the dependent variable that is caused by the independent variable. If we try to test causal hypotheses, the experimental method is the most useful and is the one that's best regarded. We'll get to what that is in just a moment. But firstly, let's briefly think about how we might want to use correlational data, observational data, to start to argue for causation. Because clearly, usual correlational studies that observe associations as they occur, cannot establish causation. If we see Instagram usage is associated with social isolation, we don't know in which direction that goes. Maybe people who are socially isolated like to spend more time on Instagram. In experiments, we would manipulate one of the variables while keeping everything else the same. So we would get some people to spend more time on Instagram and then we would see if it changes their social isolation. Looking at an example from the Gapminder dataset that we explored in class so far, we can see here that infant mortality is associated with the birth rate. More children dying young is associated with parents having more children. Why is that? I can think of at least 3 hypotheses. One causal hypothesis might be that if many children die, then parents have an incentive to have more children so that at least some of them survive. Another causal hypothesis could go in the opposite direction. So we could say, we could expect that if parents have many children, that their resources then get stretched, they're not able to take very good care of all of their children, therefore more children die. Or we could say there's maybe no causal relationship at all, but there's an underlying factor, in this case quite likely poverty, that restricts access to birth control and restricts access to healthcare. But how would we try to establish which of these competing hypotheses is true? So to truly establish it, we might want an experiment, but let's think about what we can do with correlational data first. Here we could use a longitudinal study which combines our observations of a group of participants, in this case countries, with time. And we might want to see whether changes in one of the variables predict changes in the other variables sequentially. So do changes in birth rate in 1970 predict changes in death rate in 1975 more strongly than the other way around? If that is the case, we might want to say that that is the more plausible causal direction. However, it doesn't rule out that, for example, poverty is the real cause underlying both. So an experiment would provide us with a more definitive answer if we can manage to change one variable while keeping everything else the same. So we would have two groups that are the same to start with, and then we would want to change potentially access to birth control for just one of the groups. However, clearly keeping everything the same is very hard when we study humans or when we study countries, since they are very, very diverse. So what we would try to use is the power of randomization. The notion here is, if we randomize things, so if we randomly decide which participant gets which treatment, which level of the independent variable, then differences can be expected to cancel each other out on average. So if we here randomly divide the participants into two groups, and going back to the earlier example, get one group to spend more time on Instagram than the other group, we might expect that everything else is the same between the groups. In any one experiment, that might not be true, but over the long run, it will be true. And the whole idea of quantitative methods is that we build in replication. So any one experiment might lead to mistaken results. In the long run, randomization will ensure that there is no difference between the groups. However, randomization needs to be done carefully and properly. If we, in the Instagram study, call participants to a meeting and assign the ones who arrive first to spend more time on Instagram, and then the ones who arrive later not to do it, clearly that's not random. If we do it with positions in the rooms, the ones who sit in the front, who are likely the ones who experience less social isolation, if we assign them to one group and the one sitting in the back to another group, again, we failed in our randomization. It's not as trivial as it sounds, so there's a strong reason for doing randomization, for example, with a random number generator in a computer. Once we have an experiment, a big question is whether there are confounding variables. Those are basically any factors that prevent us from establishing causation. So for example, if our groups differ systematically because the randomization has gone wrong or we actually just haven't randomized, those differences would be confounding variables. We might also, through changing the independent variable, through the way we change it, also have changed other variables. So if we do a large experiment on birth control, we randomly assign birth control to some people, and then we tell them you need to go to a healthcare provider and pick it up. We change the availability of birth control alongside the exposure to healthcare, and then we won't be able to say that any change in infant mortality, for example, is actually because of birth control. It might just be because of exposure to healthcare. If we don't have any such issues, then we have a true experiment, and that's what we're aiming for. So let's look at one more example and how we could test this in different ways. So if we have the hypothesis that alcohol increases aggression, a first step could be to do a very simple correlational study and try to compare the frequency of assault in bars and in cafes. And we might find that assaults are more frequent in bars, and then we might think that since people drink alcohol mostly in bars rather than in cafes, that this might be due to alcohol. So we might get a hunch that this causal hypothesis could be true. However, we can't establish it. Correlation is not causation. So then we could move on to an experiment, invite some people to come along, randomly give alcohol to some of them and not give it to others, and then test the level of aggression in both groups. However, we have the issue of confounding. The participants who come all the way to our experiment and then don't even get a beer out of it, they might just be frustrated, which would be a confounding factor. So a better experiment would be to at least get everyone who comes into a more similar position, give everyone a beer, but some of the participants an alcoholic beer, some of them a non-alcoholic beer. This might be quite a good experiment to test the effect of alcohol on aggression. This idea of giving people the beer without labels is the idea of blinding in experiments. So ideally, participants shouldn't know what experimental condition they are in. If it's just the participants who don't know, we call that single blind. If also the experimenters don't know, we call it double blind, and that's helpful because if the experimenter knows and has the expectation that a certain hypothesis is true, the behavior might subtly encourage the participants to then also behave accordingly. Triple blind, that's coming more into use at the moment, is that also the statistician doesn't know. So basically, in a triple blind experiment, the computer would allocate participants to one of the groups. Then those groups would just have labels, group A and group B. Experimenters and statisticians shouldn't know which group is which, and only once the conclusion has been made that group A, for example, shows a great higher level of aggressiveness than group B, it would be revealed which group was which. That takes out a lot of possible experimental bias in such issues. Because sometimes this is not literally possible with regard to the level of the independent variable. If we want to compare three types of teaching, everyone will know what type of teaching they are currently doing or experiencing. But ideally, they shouldn't know what the other levels are, so they don't know what we are comparing them against, and they shouldn't know what our hypotheses are. And if they don't know those two things, then it's pretty much as good as being blinded. So randomized blinded experiments are the gold standard for quantitative research that wants to establish causation. Why are we not only doing them? Well, in some cases, they might just be very expensive, and in some cases, they clearly are unethical. If we want to research the impact of winning the lottery, running an experiment in which we give people a couple of £1 million and other people don't receive that is probably not feasible. If we want to research the impact of substance abuse, randomizing some people into using illegal substances is clearly unethical. So we can't always use experiments. And also experiments are generally unlike the real world. They often have very sharp discontinuities. So right now, your situation changes and you get into that condition. That might just not be particularly realistic. So at times, experiments might not allow us to test for the type of influence that might exist in the real world. So sometimes we might need to argue for causation without having experimental data. And we can use logic, we can use other evidence to suggest why one direction of causality might be more reasonable to believe in than the other direction. But it's very important to recognize that that is then just an argument and we can evaluate the quality of the argument. A good criterion to evaluate the quality of research is whether people acknowledge that difference in an honest way. There's a nice middle ground job that we can sometimes use, which are so-called natural experiments. And they make use of the fact that from time to time, variables change in the real world in a way that's either actually random or at least random in the sense that it's definitely unrelated to the dependent variable we're interested in. So a couple of examples might be actual lottery winners. In the real world, some people who play the lottery randomly win. So we can use that as an experiment to test the impact of winning a lottery. When there are things like visa lotteries, where some people randomly get the opportunity to move to the United States, we could use that data between the ones who win in the visa lottery and the ones who don't to test what the impact of migration is on, for example, a life satisfaction. A similar example would be to look at students who are admitted either by a truly random ballot, or some people say also who are admitted at the margin, because you might argue that kind of the bottom 10% of students who are admitted and the top 10% of the ones who just didn't make it are basically not distinguishable. If you believe in that argument, you have found a very nice way to test for the impact of attending an elite university. People have done that and found that the difference is actually quite small when you use this as an approximation of random allocation. If you don't do it, and you just look at the correlation between having attended Harvard and having attended a lower ranked university in the US, of course you find a strong association, but then there would be a systematic difference between the groups. People assigned to student housing or to other housing might be in that situation where there's a natural experiment going on that you could do research into prejudice, for example, by looking at people who were randomly assigned to live in a multi-ethnic setting. And programs that are rolled out sequentially could allow you at a local level to test, for example, housing stability of people before and after the universal credit benefit reform was rolled out. So if researchers are aware of these things, data is collected at the right times, we can sometimes get really strong evidence from so-called natural experiments. They will hardly ever be true experiments. You can always have somewhat more complex discussions around confounding variables. But to me, they're a very exciting area of research in the social world. When we now have experimental or correlational findings, a question to always ask is what the validity is. Validity is basically our shorthand for quality of research. Commonly, we divide that concept into three aspects. The first one would be internal validity. So the question is, did the study actually show what the researchers wanted to show and what they claim they have shown? Construct validity is, do the labels that they use actually refer to the correct things out there in the world? And an external validity would be around how far the findings generalize. We will look at each of them in turn. So starting with internal validity, the main question is whether there are confounding variables. Because if there are confounding variables, if there are variables that might explain the difference but that we didn't hypothesize, then the association might just be caused by something else than what we claim it is explained by. So a current example here might be if I wanted to evaluate whether the flipped classroom teaching approach is more effective than a traditional teaching approach, I might have a real issue with confounding variables. So if I compare this year to last year, I would need to make sure that the student groups were at the same level. I would need to make sure that the motivation of the teacher was the same, that the experience level was the same. I would also need to make sure that student motivation wasn't affected, at least not by anything that's not relevant to the method. If students always enjoy flipped classroom teaching more, that would probably be fine. But if the fact that students are part of the first group, for example, affects their motivation, positively or negatively, that would be a definite threat to internal validity. Looking at construct validity, as I said, the question is, do our experimental variables refer to the right things? So the first would be the independent variable that we manipulate. One of the questions is, are we actually manipulating something else that then also introduces a difference between the groups? So I already mentioned an example there with birth control. If we give people access to birth control by getting them to walk to a healthcare provider, we manipulate both access to birth control and the frequency of exposure to a healthcare provider. Similarly, if we do a study on caffeine intake or alcohol intake, we might get people to drink a beverage that contains caffeine, we might get people to drink alcohol, but at the same time, they of course also just drink some liquid. So there we are manipulating different things at the same time. In therapy, similarly, if we want to evaluate different types of therapy, a big factor is often just spending time with a caring person. So if I find that psychoanalysis is really good compared to no treatment, I don't know if it is about psychoanalysis or if it is just about human relationships. And very often, this then leads to debates about defining good control conditions. So, what should the actual difference between my groups be? Should it be that one group receives psychoanalysis and another group just receives an unstructured talking session? For example, should it be that one group receives birth control pills and the other group receives some other offer at the healthcare center to ensure that they also go to the healthcare center? So this might be an issue with construct validity. The other issue is that sometimes we might in fact manipulate something different altogether. We might want to manipulate self-confidence through getting people to read some self-affirmation statements, but it might actually backfire, and they might see a difference between the self-affirmation and where they are, and they might actually become agitated. To figure such things out, many experiments include manipulation checks. So they say, we want to change this variable, this is how we do it, but we also need to measure if we succeeded at that. Of measured variables, so either the dependent variables in experiments or any variables in a correlational study, we need to ask, are we actually measuring the right thing? Or are we maybe measuring something quite different? This usually becomes most relevant when we measure somewhat complicated kind of mental constructs. So we might want to do a study on political correctness, and the way we devise the measure, it might just turn into a measure of political ideology. So if we do it in a way that people who make racist comments are less politically correct on our scale, actually our scale might actually not measure anything linked to political correctness. How do we figure that out? 3 concepts that we'll explore in more detail in class. One is face validity. Does this measure seem to measure what we wanted to measure? And of course, does it seem to measure that in the eyes of someone who has some idea of the research field? And that's an important first question to ask. And then there's this question of convergent and discriminant validity. So does our measure tie into the pattern of relationships that is already established? So if we know that political correctness, for example, is linked to agreeableness, the personality trait, we would expect those two to have a relationship that's convergent validity. If we theoretically expect that it is really different from political ideology, we would expect it to not be, at least not be too strongly associated with political ideology. So that would be discriminant validity. If those relationships don't show up, that indicates that we might just actually be measuring something different from what we intended to measure. The other aspect of thinking about the quality of measurements is reliability. The notion of reliability is just, if we measure the same thing twice, would we get reasonably similar results? In other areas, that's thought of as the signal to noise ratio. So if the number that I get is mostly determined by random noise and just is a little bit dependent on the thing that I want to measure, I clearly have a problem. So in this first extreme example, if my measures are just all over the place, I have low reliability, I'm just not measuring anything at all. Basically at that point I don't need to worry about construct validity anymore. if my measures are very replicable and I'm always measuring the same thing, I might still be measuring the wrong thing. So in this example, I would have high reliability but low construct validity because I'm measuring something different. And of course, the ideal is having both. Ideally, I want to have a highly reliable measure that gives me the same number every time I measure the same thing. And it should also measure the right thing. Lastly, we have external validity, where we then ask, okay, we have actually figured out that this relationship is truly valid in the context of your experiment or your correlational study, but how far does it generalize? Would it be the same with other groups of participants in other places, or is it very specific to a context? And there isn't necessarily anything wrong with it being specific to a context. We just then need to be aware of that limitation to generalizability. One important specific question in that is, what's the population that your participants came from? Were they all educated, rich, Western psychology students, or were they actually a more typical group of people from a general population? And related to that, but as a distinct question, we might want to ask, do the results apply to real behavior? That's what's meant by ecological validity. So in an experiment, there might be demand characteristics. People who come to a lab might expect to follow instructions. They might want to please the experimenter. That might mean that results in an experiment in a psychology laboratory, for example, might not predict real-world behavior as closely as we expect. That might also be because there are different stakes. So, for example, if in communication studies, I wanted to do research into the efficacy of different types of marketing campaigns, and I got people to rate certain adverts, they might actually pay much better attention to that incidental information than they would if they were just passing these adverts on the tube. So that might reduce the ecological validity of these ratings. Conversely, quite a lot of research is done into medical choices. So how do people choose between different treatment options depending on how they are presented? Possibly in an experiment, participants don't engage with that at the same deep level that they would if they were sitting with their doctor and actually making life or death choices. So there might be an issue about ecological validity coming from that perspective. When we think about how to design studies, there are often trade-offs between different types of validity, most classically between internal and external. So let's assume we are interested in reciprocity, whether people are giving back when they receive something from an interaction partner. We could do that in the laboratory. We could imagine one of these two guys is the experimenter. He gives a specific gift to the participant, and we measure what's coming back. It's nice because it's highly controlled. The only difference might be the amount that the experimenter passes on. However, we might then wonder what kind of real life situations our findings really speak to. At the other extreme, we might go to a coffee shop and buy some people a coffee and see what they do. That would be a very ecologically valid study, because unless we do something majorly wrong, we could expect their behavior to at least generalize to other coffee shops, to these kinds of social situations. But we might have lots of arguments about confounding variables in there. So quite often it makes sense to not assess the validity of one particular piece of research, but to try to look at a research program, where maybe someone has done a validation study to figure out how do we actually measure something to achieve good construct validity. Then a laboratory study to say, under highly controlled conditions, what kind of relationship do we see? And then some kind of field study to see, does this apply in the real world? Such a program of research would have a high level of validity. Any one study, almost by necessity, will have some limitations to be aware of. So, what are the key concepts to remember from this video? The first would be the idea of hypothesis testing. A lot of quantitative methods are about testing specific falsifiable hypotheses. The second is the difference between experiments and correlational studies, which really matters when we talk about causation. Experiments are any studies where we manipulate the independent variable and see whether that manipulation of the independent variable leads to a change in the dependent variable. Correlational studies are anything else, and correlational studies by definition don't allow us to establish causation. They might allow us to argue for it. Randomisation and blinding are two key concepts for experiments. In experiments, we want to make sure that the two or more groups of participants don't differ systematically. That's why we would randomize participants into different groups. Blinding means that we don't want participants or experimenters to behave in a kind of self-fulfilling prophecy, so we don't want them to know what's expected of them. And then lastly, the notion of validity is critical when we want to assess the quality of any piece of research, be it in a newspaper or in a scientific paper. Firstly, this notion of internal and construct validity. Are our measures good enough, and is our design good enough to really establish the relationship we claim to find? And then external and ecological. Does this actually apply to other settings, and does it particularly apply to real-world settings? And those are things we'll discuss using a range of different examples over the next couple of weeks. So thanks for watching. Make sure to also have a look at the other video on descriptive statistics and using the dplyr package in R, and then I'll see you in class.